prior to 1897, our model of the atom consisted of a solid sphere. If you remember from chemistry class, the Dalton solid sphere model of the atom is indivisible. It doesn't get any smaller. It's like a billiard ball. It's as small as it gets. Now, you might have the 3 ball or the 5 ball or the 8 ball or the 9 ball. They may all be a little bit different, but they don't get any smaller than the atom itself. Thomson comes along in 1897 and challenges that. He says that the atom can get smaller. There are things that are floating around inside the atom, things that we call electrons. Now, how did he get that? Where did he come up with that idea from? The idea that there's these negatively charged subatomic particles. Well, he used something called the cathode ray tube. And a cathode ray tube is the basic mechanism inside an older style TV. The TV that you see up in the corner there right now has a cathode ray tube inside it. The cathode ray tube consists of essentially an evacuated glass tube. It's this big glass tube that has all the air sucked out of it. Now, that big glass tube might look something like this. At one end of the glass tube, there would be an electrode that's hooked up to a battery. At the other end of the glass tube, well, or partway through the glass tube, there would be another electrode that's hooked up to the other end of the battery. The first electrode would end up being a negative electrode, and the second one would end up being positive because of the orientation of the battery here. A big potential difference across this would allow electrons to jump across from the negative terminal to the positive terminal. But because we have a hole in the positive terminal, they would end up just going straight through. So it's like they want to go to the positive electrode, but because there's a hole in the positive electrode, they go to it and then they just keep going straight through. They hit the screen. Now, if this is a TV, then the screen would glow. The screen is painted with a phosphorescent coating, and that phosphorescent coating will glow when a beam of electrons strike it. That causes a glowing spot on the TV. Where the glowing spots exist and what colors they are, that's what determines what the picture is going to look like on your TV. Thomson's cathode ray tube was much, much simpler. He wasn't trying to create a picture. He was just firing these beams of whatever, at the time he didn't know what they were, at the screen and seeing where they hit the screen. Now let's go back a little bit here. Prior to Thomson in 1897, lots of people had seen this. Lots of people had observed these mysterious rays. We call them cathode rays. These mysterious cathode rays that are coming from this negative terminal towards this positive terminal. This negative terminal that, sorry for all you chemistry people, this negative terminal that we're going to call the cathode toward this positive terminal that we're going to call the anode. What did you learn in chemistry? Electrons go from the anode to the cathode? Electrons go from the anode to the cathode? Well, depends on which way you look at it. The electrons are going from the anode to the cathode here, right? Depends on whether you look at it here or whether you look at it here. In the end, it is what it is. Whether it's a little bit confusing with chemistry or not, we got to live with it. Okay, the anode is that negative terminal. The cathode is the negative terminal, and the anode is that positive terminal. The electrons go from the cathode to the anode. And prior to 1897, people saw this. They just didn't know it was electrons going from the cathode to the anode. They called them cathode rays because they left the cathode and went toward the anode. Now, Thomson, he wanted to know what these cathode rays were, what these mysterious rays consisted of. So he had this brilliant idea of introducing a magnetic field down here, near the end of this cathode ray tube. When he did, he found that this mysterious cathode ray actually changed direction. He found, when he did that the cathode ray bent or started going in a circular path. That told him what? What did he conclude from that? It had a charge. In fact, specifically a negative charge. Thumb, fingers, palm points downward. We would say that these particles must be these mysterious cathode rays that nobody had ever figured out what they were before this. These mysterious rays must be negatively charged particles. Now, this says nothing about them being subatomic yet. We haven't discovered an electron yet. We've just established that they're not beams of electromagnetic radiation. They're not beams of light. They're beams of charged particles. Other people had hypothesized that before. Other people, he wasn't the first guy to come up with that idea. But he's confirmed now, at least, that they're negatively charged particles. Some of you might be thinking, well, how do we know what happens to negatively charged particles in a magnetic field when we haven't even discovered electrons yet? Negatively charged particles, right? We knew long before this about charged particles. In 1819, Oersted discovered that moving charges generate a magnetic field. That was almost 80 years before this. We knew about charged particles then. We just didn't know where they came from. So we knew what happened to charged particles in magnetic fields. We knew that these had to be negatively charged particles deflecting this way. We just didn't know where these negative particles came from, that they were electrons. We'll get there, though. Yep. How did he know that what went towards the charge? How did he know that they bent downwards? Good question. Okay. Anybody answer that? How did he know that he bent downwards? We can't see them, right? What's the screen painted with? This phosphorescent coating. When the beam of the electron strikes it, it glows, right? The coating glows. So if the glow was right here, but now the glow is down here, then it must have bent them downwards. Does that make sense? Yep. Yep, yep. Yeah, the hand rule for deflection. Thumb goes in the direction of the particles, which is to the right. Fingers point in the direction of the magnetic field, which is into the page. Palm points downward. So if they are negatively charged particles, like we're assuming they are when we're using the left hand rule for deflection, then they have to deflect downwards, and sure enough, they do. So they must be negatively charged particles. Thompson said, look, that's not good enough for me. I don't want to just know that they're beams of negatively charged particles. I want to know more about them. So he tries to do some math. Math solves every problem, right? Fc is equal to Fm. We've done this before. The centripetal force of these charged particles going in a circle is equal to the magnetic force. mv squared over r is equal to qvb. One of the v's cancels, and we're left with mv over r is equal to q times b. All right, let's calculate something. What are we going to calculate? Well, Thomson knew what the value of B was because he was the one that introduced the magnetic field, so he should know what its value is. He knows what the value of R is, the radius of the path of these electrons. He knows what the value of R is because of where they strike the screen. And he can determine what R is based on where the screen goes. But that's about all. He doesn't know what M is. He has no idea what the mass of these charged particles is. He doesn't know what Q is, the charge of them. And he doesn't know what V is. How fast are these things moving? Who knows? This is the crux of the experiment right here that differentiates it from anything anybody else had done before. This is the first thing that really gets him towards discovering the electron. The idea that these are subatomic negatively charged particles. He introduces another magnetic field over here. That magnetic field would, on its own, do the same thing as the first magnetic field, cause the particles to be deflected downwards. But what he does, in addition to that magnetic field, is introduces two charged plates, which cause an electric field. That electric field would cause the particles to be deflected upwards. So magnetic force downwards, electric force upwards. Which force is bigger depends upon how fast the particles are moving. Sometimes the electric force is bigger, sometimes the magnetic force is bigger. But for the charged particles going through at just the right speed, the forces will balance. If they're going at just the right speed, the forces will balance. Those are the ones that we want to pay attention to. The particles for which the electric force balances the magnetic force. We don't care about the other ones. Some of the other ones deflect upwards because the electric force is bigger. Forget about them. Some of them deflect downwards because the magnetic force is bigger. Forget about them. We care about the ones that go straight through because those are the ones that are going to enter this last section here and are going to allow us to do this analysis. Those are the ones we care about, the ones that go straight through, the ones that Fe is equal to Fm. Fe is Q times E, Fm is QVB. Cancel out Q's, V is equal to E over B. Thompson knows what E is. He put it in there. Of course he knows what its value is. He knows what B is. He introduced it. He knows what the value of B is. From that, he can calculate V. Now, for the charged particles that are going this speed, going straight through here and entering this last section, he now knows what V is for that last equation. That leaves him with now two unknowns instead of three, M and V. That's still not very good, but it's better than nothing. Somebody walks into this room and says, Mr. Dickie, how old are you? I said, I don't want to tell you, I'm too old. Same person says, Daniel, how old are you? I says, I don't want to tell you. Why not? I don't know, I just don't want to tell you. The person says, well, I don't feel like I've accomplished very much here. I wanted to find out Daniel's age, and I wanted to find out Mr. Dickie's age, and I don't know either one of your ages. Then Daniel says, you know what? Mr. Dickie is twice as old as I am. The ratio of our ages is 2 to 1. The guy's like, yeah, thanks. He walks out of there at least a little bit ahead of where he was before, right? He doesn't know what my age is. He doesn't know what Daniel's age is, but he knows the ratio of my age to your age, which is better than nothing, right? It tells us that, we're not going to be in first year university together because we're dramatically different ages, right? I'm twice as old as you are. Okay? We're in different phases of our lives. Okay? Thompson says, you know what? I don't know what M is. I don't know what Q is. I can't find either one of them, but I can find the ratio, and that's better than nothing. Just like finding the ratio of my age to your age is better than nothing. So he rearranges that last equation. Solves for Q over M. Let's take the M down by dividing. V over R is equal to Q over M times B. Now let's take the B over by dividing. Let's leave it up there and do another step here. Q over M is equal to V over B times R. He measures the speed of these particles that are going undeflected through the second section of the cathode ray tube. Then he measures R of the electrons over here. Then he measures B of the magnetic field strength right there in that third section. And he gets a value of Q over M. That charge to mass ratio for this beam of negatively charged particles worked out to be a value of about 1.76 times 10 to the 11 coulombs per kilogram. That value was massive, was huge compared to the highest charge to mass ratio ever found before that. What did that tell him? Here's the what did I say, 10 to the 11? Here's the climax of it all. If the charge to mass ratio is 10 to the minus 11, and that number is way bigger than any other charge to mass ratio, then the mass must be way smaller than anything else ever found. If this is way bigger, then this has got to be way smaller. If the mass of an atom is whatever, and the mass of this beam of negatively charged particles is smaller than the mass of the atom, then what do we know about these beams of negatively charged particles? They're smaller than atoms. They're subatomic. That's the discovery of the electron right there. The charge to mass ratio is so big that the mass has to be so small that it's got to be smaller than any other mass ever found. It has to be subatomic. This negatively charged particle has to be floating around inside the atom. Now we now know that they're orbiting around, right? Okay. At that time, you just thought that they were floating around in the sea of positive charge, like boats in a harbor, sailboats in a harbor floating around, or like chocolate chips in a chocolate chip cookie dough, or they call it the plum pudding model. I've never even actually seen plum pudding, so it doesn't really help me very much. But hey, does that make some sense, guys? Does that make some sense? Sorry? Yeah, maybe, yes. Yes, maybe we should do that. Maybe we should write a little nerd bedtime storybook about who's a good artist here. Maybe somebody could illustrate it for me. All right, let's do an example here. Beam of electrons passes undeflected through a 0.5 Tesla magnetic field combined with a 50 kilonewton per coulomb electric field. The electric field, the magnetic field, and the velocity of the electrons are all perpendicular to each other. How fast are the electrons traveling? This is a cathode ray tube problem, but when you're doing a cathode ray tube problem, you have to identify what part of the cathode ray tube it is. It's like there's 3 problems in one in a cathode ray tube. Oops, where's my picture? There's the one I want. We'll call this section number 1. Okay, we don't really deal with section number 1 usually. Okay, section number 2, sometimes we call that a velocity selection chamber. And then we've got the third chamber, chamber number 3 here. Which chamber are we dealing with in this question? Second one, why do you say that, Emil? Okay, there's 2 reasons that I would see that this is the second chamber. You're right. One of them says undeflected. Undeflected means forces have to balance. Okay, that's the velocity selection chamber. What's the other thing that tells me it's a velocity selection chamber? Good, you get an electric and a magnetic field. It's the only chamber that you have both of those fields. So let's set 2 forces equal to each other, Fe equal to Fm. We're going to say Q times E, the electric force, is equal to QVB. The magnetic force, Q's cancel, V is equal to E over B. Now, this equation always ends up being the same, but my suggestion would be to derive it each time because it doesn't appear on your data sheet. So be familiar with how to get it, just because you don't want to forget it when it comes time to do it on your test. E, it's 50,000 newtons per coulomb. We converted the kilonewtons per coulomb to newtons per coulomb. Should have circled that. Our magnetic field is 0.50 Tesla. Do the math there, it works out to be 1.0 times 10 to the 5 meters per second. Is that a typical speed for a charged particle? 10 to the 5, 10 to the 6? Sure it is. It's an easy question, isn't it? It's an easy question mathematically. It's an easy question if you know where to go with it, if you know that it's a velocity selection chamber. That's the real trick with this. It's not doing the math, it's knowing what math to do, right? Okay, take a look, please, at the questions on 756, and I'm going to give you literally just a couple of minutes to work on those questions. You won't finish them up here, okay, because I'm only going to give you a couple minutes. And then we'll try to get one more example in here, okay? Take a look at one more example here, 15.2 and 758. When a beam of electrons accelerated to a speed of 5.93 times 10 to the 5 is directed perpendicular to this magnetic field, they go in a circular path with this radius. What's the charge to mass ratio? Which section of the cathode ray tube is this? 1, 2, or 3? We've got a magnetic field. It's going in a circle. Which section is it? It's the third section, right? Sometimes we call that the main chamber. In that third chamber that we sometimes call the main chamber, we say Fc equals Fm. Fc is equal to mv squared over r, which is equal to qvb. One of the v's cancels. We're left with mv over r is equal to q times b. Now, we want to find the charge to mass ratio, q over m. To do that, we've got to take the m down by dividing. And then the b has to go down by dividing. So it becomes q over m equals V over B times R, right? The M went down to the left side, the R went down to the right side. Does that make sense? V is 5.93 times 10 to the 5, a pretty typical speed for a charged particle. B is 100 times 10 to the minus 6 Tesla. And R is 0.0337. When we solve that, remember, we're not going to get charge. We're not going to get mass. We're going to get the ratio of charge to mass, which works out to be 1.76 times 10 to the 11 coulombs per kilogram. Okay? So again, none of these are too hard, right? Neither of the problems that we've done as practice problems haven't been very difficult. It's just that you have to identify what to do. Once you see what you got to do, then it's not that hard to do it. Okay, the trick is knowing what to do in the first place. You comfortable with that? Okay, your homework for tonight, practice problems on 756 if you haven't finished them already. And in addition to that, I'd like you to do the practice problems on page 758. Okay? 756 and 758. That's it for today.